Navigate ka.
Dearest classmate, I will Chapter 5, 5.4 Energy Delay Optimization. Minimizing the energy. The minimum energy point is the least energy that an operation will consume if a delay were unimportant. It occurs in sub-threshold operation where VDD is less than the voltage threshold, sub-threshold. The minimum energy point typically consumes an order of magnitude less energy than the conventional operating point, but runs at least 3 orders of magnitude more slowly. A power delay product, or PDP, is simply energy. Next. John von Neumann, a Hungarian and later American theory and applied mathematician, physicist, inventor, polymath, and polyglot, said that thermodynamic minimum of energy per elementary act of information was kT ln 2. It was supported by James D. Meindel, a director of Joseph M. Petit Microelectronics Research Center and Marcos Nanotechnology Research Center and Petit Chair Professor of Microelectronics at Georgia Institute of Technology in Atlanta, Georgia. He said that the minimum voltage is equal to 2Ln 2Vt, or is equal to 36 millivolts at 300 Kelvin. Next, this is the minimum energy point. It says here that at this point, yun. Next, this is the formula for the duty cycle and the energy in switching, leak, and the total energy. Next. Minimizing energy delay product. The energy delay product, or EDP, is popular metric that balances the importance of energy and delay. Minimizing energy under a delay constraint. Energy under a delay constraint is also minimized when leakage is about half of dynamic power. However, the curve is fairly flat around this point. So, many designs operate at a lower leakage to facilitate power saving in sleep mode. Next. So we go to 5.5, low power architectures. Next. First is the microarchitecture. Energy efficient architectures take advantage of structured design principles of modularity and locality. Memories have a much lower power density than logic because their activity factors are minuscule and their regularity simplifies leakage control. Such heterogeneous architectures, combining regular cores, specialized accelerators, and large amount of memory are growing of importance. Presently, programmers are having trouble taking advantage of many cores. Time will tell whether programming practice and tool catch up or whether microarchitectures will have to yield to the needs of our programmers. This is parallelism and pipelining. This is a normal function unit. When you use parallelism, you're using a multiplexer. Replacing a single function unit with n parallel units allow each to operate in 1/n frequency. A multiplexer selects between the results. Now, the voltage can be scaled down accordingly, offering a quadratic saving in energy and expense of doubling the area. The next is pipeline. Replacing a single function unit with an n-stage pipeline unit also reduces the amount of logic in the clock cycle at the expense of more registers. Again, the voltage can be scaled down. The two techniques can be combined for even better efficiency. Next. This is a power management mode of an Intel processor atom. Next. The worst case power that a chip may consume can be a factor of 2 or more greater than the normal power. Code triggering maximal power consumption is sometimes called thermal bypass because it seeks out to burn out the chip. To avoid having to design for this worst case, chips can employ adaptive features, throttling back activity if the issue rate or die temperature becomes too high. Power management results in substantially lower power consumption during idle mode and active mode. The transition between idle and active may require multiple cycles to avoid sudden current spikes and excite power supply resonances and cause excessive supply use. Pitfalls and policy. Now, there are different types. Oversizing gates. Oversizing gates is they said that it increases the power consumption, but it does not. Designing for speed without regard to power is a lot better than than not designing for speed. Pero it takes more energy. Reporting power at a given frequency instead of energy per operation. Reporting power delay product when energy delay product is met and failing to account for leakage. The historical perspective. This is Colossus. Brought online in 1944, was one of the world's first fully electronic computers. The secret machine was built from 2,400 vacuum tubes and consumed 15 kilowatts as it worked day and night decrypting secret German communications. The machine was destroyed after the war, but a functional replica was built in 2007. Next. The next one was MOSFET. MOSFET entered the scene commercially in around 1970. Though NMOS circuits use depletion load, negativity, NMOS full acts as resistive loads. So each gate with an output of zero dissipated potential power. This is an example of an NMOS. This is an OR gate. CMOS circuits made their debut in watch circuits, where their key ability to draw almost zero power while not switching was critical. Swiss watch uses CMOS. It was not until the mid-1980s that the ever-increasing power dissipation of mainstream circuits, such as microprocessors, forced a move from NMOS to CMOS technology, again despite density and arguments. Patrick P. Gelsinger, Chief Executive Officer of VMware as of September 2012, first Chief Technology Officer of Intel Corporation and former Senior Vice President and General Manager of Digital Enterprise Group at Intel. On February 5, 2001, he gave a keynote speech at the International Solid-State Circuits Conference. He said that, in the increasing power consumption of CMOS, in 2001, it would be 4,400 degrees Celsius. And by the time that it is in 2015, it would be as hot as the sun's surface. Kung hindi tayo magbabago. Next. So, they started looking for solutions. Clock gating was first widely applied technique for power reduction because it's relatively straightforward. Power gating was initially applied to low power battery-operated systems to increase the standby lifetime, but is now required for leakage control, even in high-performance microprocessors. Dynamic voltage scaling is commonly used to support a range of power and performance trade-offs. Body bias has been used for leakage control in applications such as Intel X-Scale microprocessor, the Transmeta FP Shield microprocessor, and the Toshiba MPEG-4 video codec. Clustered voltage scaling was also used in video codec. The move to CMOS technology was really the last major movement in mass market semiconductor technologies. Today, no one has come up with better devices. Thank you.